Welcome to Module 3 of our video on gravitation. In this module, we will explore topics such as free fall, the feather coin experiment, acceleration due to gravity, escape velocity and orbital velocity, equations of motion for freely falling bodies, and mass versus weight. Free fall occurs when an object is solely influenced by gravity. Any object acted upon only by the force of gravity is in a state of free fall. Galileo disproved Aristotle's idea that heavier bodies fall faster, suggesting that the speed of fall is proportional to weight. Robert Boyle's feather coin experiment demonstrated the principle of free fall in a vacuum. By removing air resistance, he showed that a feather and a coin fall simultaneously. The conclusion is that acceleration for freely falling bodies is the same, regardless of their masses. The force of gravitation, acting on a body due to the Earth, is the force of gravity. When an object falls toward the Earth, the acceleration involved is called acceleration due to gravity, or g. We derive the formula for g as gm over r squared, and its value is approximately 9.8 meters per second squared. By substituting the values for the gravitational constant g, mass of Earth m, and radius of Earth r, we calculate the acceleration due to gravity g to be 9.81 meters per second squared. Note that g is slightly higher at the poles and lower at the equator. The value of g varies with height and depth. The formulas shown illustrate how acceleration due to gravity, denoted as g prime, changes at a height h above the surface and at a depth d below the surface of the Earth. Escape velocity is the maximum vertical velocity needed for a satellite to leave Earth's gravitational field. Orbital velocity is the horizontal velocity that keeps a satellite in a stable circular orbit around the Earth. Escape velocity is the square root of 2 times the orbital velocity at a certain height. Let's practice some problems. First, we calculate escape velocity using the orbital velocity relationship. For the second problem, we determine the radius of the Moon given its mass and gravitational relationship to Earth. The standard equations of motion can be adapted for freely falling objects by replacing acceleration a with the acceleration due to gravity g. These equations help calculate velocity and height for objects in free fall. Here are 2 practice problems using the equations of motion for freely falling objects. The first calculates the initial velocity required for an object to reach a certain height, and the second determines the time period to reach maximum height. Mass is the amount of matter in a body, a scalar quantity that is constant and non-zero, measured in kilograms. Weight is the force of gravity pulling the body towards Earth's center, a variable vector quantity measured in newtons. We also practice calculating mass and acceleration due to gravity based on weight. Let's solve a final practice problem. We first calculate the weight of a person on Earth, then calculate their weight on a planet where the acceleration due to gravity is half that of Earth. We also determine how far a man must go from the Earth's center to quarter his weight.